How could you ask?
Asking between elements, which one has higher energy ionization.
Perfect. Which of these four options has the highest energy of ionization? Sodium, magnesium, potassium, or chlorine? Chlorine. Because it's the furthest to the right in the same period, right? Which of these has the highest energy of activation? Lithium, sodium, potassium, or I think it's rubidium. Lithium. Why not all the way down here? Because remember, it goes down as we go down because it's further away. So lithium would have the highest, right? What about lithium, carbon, oxygen? Oh, no, that's not. That was, yeah. Maybe. How about this? Sodium, magnesium, phosphorus, or oxygen? Oxygen, because it's higher. Not only is it further to the right, right? But what is it? It's also the highest. So out of all of those options, oxygen is the biggest one, right? That does not mean you need to memorize the periodic table, but it does mean you need to appreciate when it comes to energy of ionization, how does it change? Right?
Does this mean that helium trumps all? Like it's...
It would, except for the fact that, well, yes, the energy of ionization for the noble gases is very high. Yes. That's one of the reasons why it doesn't react. Because even floating around in the atmosphere, it is hard to strip away electrons from a noble gas. They don't like it because they're deep inside that well. They are at a very low energy state because their outer shell is already full. They don't need anything. So forcing them to react, forcing them to ionize is hard. Metallic character. It's like, reminds me of like going to a civil court needing a character witness. Like, would your friend, or I had a friend who went to work for the Nuclear Regulatory Commission in the Navy, and they had to do a background check, and so I had a guy from the Navy come and interview me about like what I felt about the character of my friend, like would he steal? You know, do I know of any instances where he is like, and none of this was like, because we're going to arrest him. No, it was just like, we don't want to put a guy in a position of authority and trusted with state secrets if he's, you know, frequently shoplifts candy bars from a gas station. Like, it's a minor thing, but if you're willing to do minor things, you probably wouldn't feel too bad about maybe sneaking away with some confidential information or something, right? So, character witness. Question?
I was just going to say that metallic characters tend to lack heart.
So do straw characters, actually. Or so, we're looking for brains. That was the brains, yeah. Yeah, you're right. So, metallic character. Metallic referencing metals, right? So the metals, the ones in the lower left of the periodic table, are the ones that are... So what do you think we mean by metallic character? What are some of the aspects, what are some of the ways that we described the metals as a group?
Shiny.
Shiny, ductile, right? Malleable.
High melting temperature.
Those things are probably not as important with respect to what we're talking about here. So what's the other things that we describe melting, metallic things having? High melting points, good conductors. Metallic character decreases as you move to the right. It increases as you go down. Why? Because as you go down into the metals, you're getting into more and more dense, you're getting into even better and better conductors. As you move up and to the right, you're getting into lighter and lighter things, you're getting into poorer and poorer conductors. The metallic character of an element is more related to things like, does it conduct electricity, density, things like that. Less how shiny it is.
It's a magpie here.
A magpie character? I don't know if I get the reference.
Oh, magpies go for things that are shiny.
Ah. How attractive they are to magpies. Yes, sure. Sure. Or crows, for that matter, in that case.
Squirrel.
Or raccoons. Raccoons like shiny things, too. That's it. It's chapter 4. So, do we have questions about this? Here's a neat thing about quantum mechanics. When I got my PhD, I had to take a course on quantum chemistry, and out of all of the classes that I took, it was the one that scared me the most. Walking into it, and it was also the one where I learned the most. It was really neat. Because the thing about quantum chemistry, quantum mechanics in general, is that you have to take the way you think the world works and put it on a shelf. Because it doesn't actually work that way. A lot of quantum mechanics is actually counterintuitive. Because we interact with the world on a macroscopic level. Remember when I told you we never really touch the desk? It's because you never really do. So if we never really touch the desk, if our atoms are so much full of empty space, and the desk is so much full of empty space, why can't I just reach through the desk like Vision couldn't do in the stupid movie? Why can't I just reach through the desk? I recently saw Infinity War, and I can understand why there were some arguments about just some EP arguments online about the Vision and the Hulk, but that's totally, so that's a reference because he got neutered very early in that movie when his primary powers was completely neutered. He couldn't phase. Sorry if that's spoilers. But why can't I do that? Why can't I reach through this desk?
Not Dr. Strange.
Because I'm not Dr. Strange. Or the Vision, for that matter. There's a good reason, though. The atoms that make up the surface of my finger, even though most of that is empty space, right? There is also the electron cloud that surrounds the atoms of all of those molecules, right? There is also an electron cloud that surrounds the atoms of all of the atoms of the molecules that make up this desk, right? And what do we know about negative charges and negative charges? They repel. So, literally, the force that I feel when I'm pushing against this desk is the repulsion of the electrons on the surface of my finger and the electrons on the surface of that desk. Those clouds do not want to touch. And the more force I put into forcing them to, the more they will push against each other and deform, mostly the surface of my fingers because the desk is really hard, but they never actually touch. If they did, I would have a problem. Because suddenly, my hand would be covalently attached to the table. And that would be bad. But when we think about it, I'm touching this table. I can feel this table. But I never actually touched it. It's neat, it's counterintuitive, and there's a crap load of calculus. So, explore that at your own risk. But quantum mechanics, quantum chemistry is really neat, and I'm not going to keep you here any longer and bore you with it. So, I know you have till Thursday before class, but if you can, please try and finish your homework tomorrow, because I will try and grade everyone's homework tomorrow so that we can maybe take a peek before the tests open on Friday. Right? Okay?
After she shed the dead weight, my wife was working in the physics department at NMU.
Okay.
Dr. Carlos, I can't remember his name, but it was very interesting, the paradoxical elements of quantum mechanics in that they were trying to create a carbon structure inside a container that would allow them to store more hydrogen than the container could hold at lower pressure. Yes, and with lower temperature. because somehow this is what I don't know if I ever understood it,
Right.
but it's just interesting. You can put more of a substance in, but to do that, you have to put more of another substance in, taking away some of the area. And the way I'm guessing from what was tried to explain to me is that it brings the nucleuses closer together.
Maybe, I would do it. It could also be simply a way of entrapping certain gases into a matrix that is a pseudo-solid, whereas normally they're gases. And so if you do so because of the physical properties of it, instead of actual pressure and temperature, then you'd be able to skip the normal universal gas law for conversion and storage. But that's just an educated guess, because I don't know how you'd be able to do that. But it'd be similar to when you get sublimation, where something goes from a solid straight to a gas without a temperature change. That's all entropy. So if you spent enough energy, I could see how you could maybe organize a gas into a pseudo-solid without changing the temperature of it. But I don't know how you'd actually accomplish that.
Well, it's actually a liquid, I think, the helium at that point.
Okay.
But I mean, even those definitions sort of tend to break down.
Yeah, well, I mean, it's the thing about, like, if you think about individual atoms as pendulums, which is the whole basis of quantum clocks, is that an atom is a pendulum, so the oscillation of the atom is the pendulum of a clock.
Right.
That's the way quantum clocks work. But if you then think about what that means is that an individual pendulum, like an actual pendulum swinging by, it doesn't have an infinite number of spaces that it can occupy. Except at a macroscopic level it does.
You're talking about quantization?
Well, yes, which is what quantum mechanics is how we define into quantized segments all of reality, as opposed to an infinite number of possibilities. So a normal pendulum that's swinging back and forth, there is an infinite number of spaces where it could occupy along that span, right? Except that if it was a individual atomic pendulum, it wouldn't. It would jump from here to here to here to here, and then back again. But it would never occupy the spaces in between.
Right.
Because that's the way quantum chemistry works. That's the way quantum mechanics work, is you can only exist in certain states. But the moment that you added two atoms together as your pendulum, it would more than double the number of places that it could exist, because you have the additive and subtractive effect of the states of all of the atoms found within. And so what that means is that now instead of just being 4 places, it can be in 10 places. Add a third atom, and now it can be in 36 places. And so you get to where you have millions of atoms inside the actual pendulum on this clock, and that gives us the illusion of an infinite number of spaces. But what it means is that if you actually did really zoom in, you'd have to really zoom in. But eventually you would get to a part where you could, if you had an infinite accuracy, measure that there is actually a space here where the pendulum never is. Because even after we add all of the atoms that make up that pendulum, that particular space is not a possible outcome.
So,
and that breaks our understanding of macroscopic